So particle having velocity coordinate vx1, vy1, vy1, vz1 double prime. So basically these particles are a group of particles having velocity coordinate this, and those, and number of those group of particle is this. Okay, so after collision, uh, few of the group of, among those group of particles, few of the particle changes to this velocity coordinate. Okay, so that number is calculated in this way. Okay, see this vx1 double prime, vy1 double prime, vz1 double prime, and this probability that number of particle whose velocity coordinate is double prime to change to this vx vy vz. Okay, so in this way, we will obtain how many number of particles among this group of particles changes to this velocity coordinate. Okay, and this group of particles having velocity coordinate vx1, vy1, vz1. Okay, again we can consider some other group of particle having velocity coordinate vx2, vy2, vz2 double prime, and those number of particles are these. Okay, and after collision it changes to, after collision few of among this number of particles, few of them changes to this velocity coordinate. So that also, and so that number of particles also calculate in this way. So basically this distribution function in this case it just become a variable. Okay, because it contains some variable terms. Okay, so in general number of particles having velocity coordinate vx, vy, vz which has been formed after collision is calculated in this way. Okay, don't confuse that why this Fermi distribution is uh, this distribution function is just outside, and here in this case, in this case this distribution function is inside of this integral. Okay, so we have discussed both these. Okay, so basically this signifies that number of particle having velocity coordinate vx, vy, vz which has been created after collision. So there are many number of particles. So basically there are many group of particles. Okay, variable, having variable velocities. Okay, so after collision they changes to this velocity coordinate. Okay, again among these group of particles having velocity coordinate this, it changes to this. Okay, so so basically these things happens basically due to collision. Okay, so uh, rate of change of distribution function due to collision will be this. Okay, this b basically signifies that group of particle having velocity coordinate vx, vy, vz which has been formed due to collision. Okay, and this a signifies that among those group of particle having velocity coordinate vx, vy, vz, few of them changes to some other velocity, some other uh, velocity coordinate. So difference is basically signifies that group of particle having velocity coordinate vx, vy, vz which has been formed due to collision. Okay, okay. So basically we add both of the both basically now we are going to add both variation in our distribution function. This is basically due to drift, and this is basically due to collision. And under equilibrium, say after a few moment of time when system comes to an equilibrium. Okay, so different position coordinate have some different velocity coordinate. Okay, but it will be fixed. Okay, some another say x1, y1, z1 velocity coordinate, position coordinate have velocity coordinate px1, vy1, vy1, vz1, and some other position coordinate it has with that fixed velocity coordinate. So when system come in equilibrium, these things happens. Okay, basically we can see some kind of river flowing. Okay, some kind of say waterfall is flowing. Okay, so uh, when we see that waterfall, okay, the pattern of flowing water is just same. Okay, just at the peak of the waterfall is velocity is quite low, but just when it just fall at that places velocities are quite high. Okay, and when just it strike the surface, then few of the water just jump, just scatter here and there, make some kind of clouds. Okay, so those things are totally although whole system is non-equilibrium, but but we can see that at different location things are almost constant. Okay, things are constant. So under condition of equilibrium we add both the term and we just take it zero. Now we just write the term, this drift variation term. Okay, and this collision variation term. Okay, and few mathematics, this vx, vy, vz, and alpha x, alpha y, alpha z. So this gets alpha vector dot this gradient of gradient prime f, and this v vector dot mm, grade of V. Okay, so this grade prime is basically nothing dv dx y dv d sorry d dvy and d dvz. Okay, this prime signifies this, and non-prime signifies simply d dx d dy d dz. Oh, you can follow in your MSc classes. Okay, now finally, uh, back to our question, Boltzmann transport equation that we are trying to achieve. Okay, so from the beginning only we had considered an electronic system. So now it will be not much more difficult if I am going to change this equation on if I am going to change these equations. Okay, basically I'm not changing this equation. This is basically a generalized equation. Okay, this v vector is basically is some kind of velocity, and is some kind of acceleration, and the source of this velocity or acceleration may changes, or might be it this source of velocity and acceleration may be due to electric field, or maybe due to temperature gradient, or maybe some kind of magnetic field. So it can be anything. Okay, so let's discuss. So basically this is a Lorentz force. Okay, and this E vector and this H vector is E vector is electric field, and H vector is magnetic field. Okay, and this V vector is basically velocity of a charged particle, and in our case we are considering an electron. Okay, so writing in it in a coordinate wise, so we have written it, and that's back. We can see that we can obtain this alpha x, alpha y, alpha z, because this F vector is equals to m mass into acceleration. So this alpha x, alpha y, alpha z can be put at here, and so we are doing that only. Okay, so that's all. So we are just plug these alpha x, alpha y, and alpha z is 0, so it is not, so it is missing. Okay, uh, and let's reduce our system. Uh, let's reduce our situation more simpler. Okay, we are just considering that only electric field is applied, and that is also in along x direction, and there is not any kind of magnetic field is there which is subjected to our system. So our this Boltzmann transport equation changes to in this form. Okay, so it looks more uh, what we call more simpler form it takes, because we are just considering that our electronic system is subjected to only electric field, which is also directed along x direction. Okay, so this is our Boltzmann transport equation for the electron. Okay, so we are obtain our Boltzmann transport equation, but our we had said that how our distribution function changes under the influence of such kind of fields. So till now we are not obtained at that point. So we are going to we are going to that point only. Okay, so we are so but we had obtained one. So we had completed one of the steps. So this is that. Okay, so Lorentz assumes that collision of electron is elastic, the scattering of electron is isotropic. Okay, collision of electron is elastic. So uh, we are considering that when electron collide with some kind of scattering center, then at the time we don't lose any kind of energy. Okay, and a scattering of electron is isotropic, uh, that is scattering is not promoting some kind of direction, that it will not promote that. Okay, after colliding it will prepare this direction only. So we can say that it is something like spherically symmetric potential type thing. Okay, this point signifies. Okay, another is the equilibrium distribution function if does not change due to electron scattering. Okay, under equilibrium this distribution function don't change. Okay, so but that distribution function till now we are not obtained, we have to obtain that. Okay, so the difference of equilibrium function of the difference of equilibrium function and distribution function from equilibrium. Oh, sorry. Okay, so this one is f is basically distribution function under the influence of our external fields. Okay, and f0 when we don't apply any kind of external field. So basically this f0 is simply a Fermi Dirac distribution function. So when we don't apply any kind of external field. So at that time, uh, our distribution function is simply Fermi direct distribution function. Okay, and this is relaxation time. So basically, uh, when an electron under the influence of some kind of field, okay, when it comes, okay, so that electron just move, and from one scatter, and just it move and collide to some kind of scattering point. Okay, again after colliding to scattering point, again it regain its velocity, and again it collide to other scattering point. So time taken from one scattering point to another scattering point, uh, that time is this relaxation time. Okay, so under, so just we can say that just when we just apply, when we just begin our external field, at that time distribution function is f0. Okay, and it remains in f0, but after time tau, that distribution function f0 changes to f. Okay, due to some kind of collision. Okay, in this way we can imagine about the scattering point where we are where I am just talking about this collision, but we have to talk in terms of external field also. But for just for understanding, I had considered this. Okay, but I hope it is clear now that for uh, before t equals to 0, we have distribution function this f0, and it remains f0 until tau. This is relaxation time. When tau comes, when the time t equals to tau, then at that time our distribution function changes to this. Okay, so df by dt collision is this. Okay, so obviously we don't have to talk about this external field. I'm just talking about df dt by collision. So under collision, if I say then discuss that just before collision, having distribution from f0, and it remains f0 until our particle don't collide to some kind of scattering point. Just when it collide to some kind of scattering point, then its distribution function changes. Okay, so the time when it collide to that scattering point, that time is tau. So we can write in this way. Okay, so this d by dt changes to minus f0 by tau. Okay, so we plug that, and that's back. We obtain this f. Okay, we obtain this f. So by the application of this solution, we can obtain more refined results for electrical and thermal conductivity. So it has great application. Great application what? It is very much important. Without this, we can't explain this electrical conductivity, thermal conductivity. We can't explain, because basically the electrical conductivity or thermal conductivity, this all makes our system in non-equilibrium. Okay, just it comes in under some kind of external field, and even it collides also. So our distribution function basically changes. Okay, see how these distribution functions are very important. Okay, uh, I'm not talking about this distribution function. See this. Okay, when people calculate this electronic specific heat, okay, without consider any kind of Fermi Dirac distribution, so they obtain this one. Okay, that using MB statics. Okay, but experimentally people have found that such kind of curve. Okay, so but not able to explain why it's so. But when we apply in our calculation Fermi Dirac statics, so this it just meet with experimental results. So we can understand how much important these distribution functions are. So similarly, when we apply some kind of external field or some kind of temperature gradient, so at that time also our distribution function changes, and it takes in this form. So it is also very important. Okay, I hope it is clear. Now let's generalize our this result more. Okay, let's generalize it more. Okay, so when steady state is reached, okay, when steady state is reached, okay, so at that time this distribution function, okay, this distribution function f0 is just constant. Just I had taken just few minutes ago example of a waterfall. Okay, uh, although it appears that everything is dynamic, but when we take pictures, okay, and just take pictures of every day, and you will see that nothing is there. At every point velocity coordinate is fixed. Okay, so velocity coordinates are fixed. So that's why while differentiating under a steady state, when it is reached, so it will be 0. So basically we'll obtain so basically our Boltzmann distribution function reduces to in this form. Okay, and now just what we do that 1 by m df0 by dvx. Okay, and this basically that's df0 by de and de by dvx. We just write this de by dvx and df0 by de. Okay, so uh, dv by de by dvx, that term brings the group velocity vx. Okay, and df0 by de, you can follow, it's simple. Okay, I written this. Okay, 1 by m df0 by dv x, and that's back 1 by m de by dvx df0 de. So this basically makes group velocity. So in this way we obtain our distribution function. So that's our distribution function, and this basically we have taken this e, but basically this is in charge of an electron and it is negative, so modulus would be negative. And this tau is basically relaxation time, that um, time taken by an electron just after scattering, when it just reaches to another scattering point, the time taken, okay, to reach another scattering point, the time is this tau. Okay, so applying a homogeneous electrostatic field E vector which generates a directional current, okay, and causes the distribution function f to deviate from the equilibrium distribution function f0. Okay, so that's all. So now we have one distribution function, and this distribution function is basically due to some kind of when we apply some kind of external field or temperature gradient and whatever. Basically in this case we are our this generalized treatment reduces to this. Okay, basically not this one is not generalized. Okay, this one, yeah, this one is generalized form, and we had considered that electric field is along x direction and not considering any kind of magnetic field. So under those effects, uh, we had finally obtained our distribution function that we will use. Okay, uh, when our system is in some kind of an external field. Basically this type of distribution function will be used uh, when our electron is in motion due to some kind of an external field. Okay, so it have also some importance, same as in Fermi Dirac distribution function, okay, which plays a very important role in to explain this electronic specific heat. Okay, don't get confused. Okay, this is the case where we don't apply any kind of external fields. Okay, at that time we are calculating this electronic specific heat. Okay, and at that time when people try to calculate electronic specific heat, then they fails to obtain, because basically they obtain such kind of curves. Okay, but experimentally people are getting this. So after when they had considered the Fermi Dirac distribution, so they had obtained this. The experimental and theoretical both meet. So how much important this distribution function we can understand. Similarly, when we apply some kind of external fields, okay, at that time also we want some kind of distribution function, and that distribution function is that. Okay, thank you.